Hello and welcome, class. We are continuing our discussion on the 3D shapes of molecules and the implications that they have, these geometries have, on the properties, the characteristics, the nature of the molecules that we have been observing. So today we are going to return to a definition that we have previously discussed, that of polarity. Previously, we only really acknowledged polarity as an existing thing between two different atoms, but here today now we are going to acknowledge that these bonds exist in larger molecules, and the polarity of the bonds are going to have some really fascinating impacts on the physical and chemical properties of matter. Namely, we're going to get into intermolecular forces. Alright, so as a review, electronegativity is the measure of the ability of an atom to stabilize a negative charge. So this we've seen a definition for before, but just as a brief review, these atoms that are in the upper right-hand corner of the periodic table have very high effective nuclear charges, and as a result, they are going to be very electronegative. The elements that are in the lower, we can see left-hand side of the periodic table, all of these pink elements have very low electronegativities because they have very low effective nuclear charges. Alright, so the implication we talked about before, the result of these electronegativity values, were that of nonpolar bonds. If the two bonds have very similar, let's say, electronegative values, we're not really going to see a strong pull towards one atom inside of the chemical bond, right? The bond is going to be evenly spread out, evenly dynamically shared, and so we see a nonpolar bond as a result. If we observe elements that have, or that are bonding together that have very different electronegative values, here's where we're going to see some, or like an example of a really polar covalent bond, where one of the elements, due to its high effective nuclear charge, is going to be able to stabilize the electron pair a little bit better, and so the electron pair is going to hang out on that atom a little bit more. Last but not least, we observe the case, what happens when something like a metal with an incredibly low effective nuclear charge partners with something that is fairly electronegative. We see an ionic bond as the result. So the definition of an ionic bond can be explained using electronegative differences, just like nonpolar and polar covalent bonds were. All right, so that's our brief review. And now we're going to start looking at these bonds as they exist inside of larger molecules and tying yesterday's lecture of geometry into the mix. Alright, so a molecule on the whole can be polar or nonpolar, just like how the bonds inside can be polar or nonpolar. A polar molecule can only result from a really special case where all of the polar bonds that are present inside of the molecule, so you're going to need polar bonds to make a polar molecule, but they are also going to be asymmetrically or unevenly distributed around the central atom, creating what is known as a dipole moment around the central atom. And we're going to illustrate what this looks like in a second. Nonpolar molecules can be formed in two different ways. Either the molecule is made up of nonpolar bonds, or it does have polar bonds inside, but they are pointing in opposite directions, and so the moment of the polarity is going to cancel out across the whole molecule. All right, so let's look at three different examples. Each of these molecules down below kind of illustrates one of these three cases. So our first case is the molecule of water, right? Oxygen in the center, two hydrogens off to the side. Now the bond polarity present here, just to go backwards, and I'll clean this up, we have oxygen and hydrogen, which are pretty far apart on the periodic table. We would expect there to be a pretty large electronegativity difference, and we can confirm this by looking at the difference between 3.44 and 2.20. This difference is greater than 0.5. This means that we are working with a polar bond. The bonds themselves are polar. You know what, I'm gonna actually change color so I can work with the red a little bit. The color, or direction, sorry, of the pull is up towards our oxygen. So the electron pair, the bond that exists, is going to spend more time on oxygen since oxygen's better able to stabilize the electron pair. Same thing with the bond over here on the left. So we're going to end up with a little residual positive charge on these hydrogens, a little bit of a negative charge on the oxygen. The way that we represented this in chapter 6 was by writing a lowercase delta, right, this little d, representing a partial change, and there's a little bit of a positive charge here. And on the other hydrogen, we see the same thing. The oxygen is going to be partially negative. Now, because the pull of the electrons is not, or they don't like symmetrically cancel out, we have kind of a net pull upwards for the electron density. We can see that there's a upper location in the molecule right up here is going to be mostly negative, and the location down here is going to be mostly positive. This is what we call a dipole moment. Dipole meaning that there are two different locations. Polar meaning that we can draw this like nice arrow kind of up through the center, saying that this is like the north pole of the molecule in terms of charge, and the lower section is like the south pole of the molecule, right? So two different direction, like there's a distinct directionality, that's what I want to say, for where the charge is being distributed. Up north is negative, down south is positive. So we would say that water is a polar molecule because it is made of polar bonds, and the polar bonds result in kind of a distinct north and south end of this molecule. Our next example is that of BH3. BH3, where our B is in the center, H's are off to the side like so, we can see is an evenly spread kind of molecule, whereas our water was bent. The BH3 is trigonal planar, so everything is nice and evenly spread out in 3D space. The electronegative difference, if we go backwards again, between boron and hydrogen, we can use to establish whether or not the bonds inside of the molecule themselves are polar. Right, in water's case, the OH bond was very polar. In the BH3 case, the difference between the electronegativity value of boron, 2.04, and hydrogen, 2.24, is so negligibly small. Right, this is definitely a value difference that is less than 0.5, and so each of the bonds inside of BH3 we would say are non-polar. Since each of these bonds is non-polar, there is no north end, there is no south end, everything's evenly distributed. So not only do we have non-polar bonds, but we also have a non-polar molecule. All right, so far we've looked at the case where we have polar bonds that do not cancel out. We get a really nice dipole moment, right? That was our water example. The nonpolar molecule case that results from nonpolar bonds inside of the molecule was our BH3 example. Now let's look at the last case. A molecule that contains polar bonds, but the dipole moments are going to cancel out. This example, or rather the molecule that gives us a good example of this, that honor goes to carbon dioxide. Carbon dioxide, which is a central carbon surrounded by two oxygens with double bonds, in order to form a really nice stable geometry, according to Vesper theory, we're going to get a really beautiful 180 degree spread from oxygen through carbon to oxygen. So this is going to be a linear molecule, evenly spread out, no lone pairs kind of distorting the shape of the electron density inside of the two double bonds. So again, really nice linear conformation here. We have to establish whether or not the bonds inside this molecule are polar. So carbon and oxygen. Let's come back to our table one last time. You can see carbon is here, oxygen's right here. Now the difference between the electronegativity values between carbon and oxygen is greater than 0.5. So because we are working with an electronegativity difference greater than 0.5, we are working with polar bonds. The polarity of the bond we can draw kind of like how we did with the hydrogens and the oxygens in the water case. The pull is going to be towards the oxygen and away from the carbon. This will leave a partially positive value inside of the carbon, so hence this little plus sign on our arrow here. And the same thing's going to occur on the right-hand side, right? Our pull is going to be away from carbon towards the oxygen, a little bit of a plus hand sign here, or a plus sign on the back end of our arrow. This means that we are going to have a partially negative oxygen on the left, a partially negative oxygen on the right, and a partially positive carbon in the middle. Now, unlike water's case, where we can, again, kind of establish there's a clear north end and south end where there's like a clear line being drawn between where it's negative and positive, in the carbon dioxide case, we have a central location that is positive, and we have a negative and a negative on either side. So there's not one really nice north end and south end on this molecule. There's no one arrow we can draw and cut it in half in any way and say, here's the north and here's the south. For that reason, we say that the two ends of the molecule that are partially negative cancel each other out. There is no north end, there is no south end. Because the negative charges are perfectly 180 degrees apart from one another, we actually get this canceling of the dipole moments, mathematically speaking. The magnitude of the distribution to the right is equal to the magnitude of the distribution to the left. This means that they are going to cancel each other out. Yes, the bonds inside of this molecule may be polar, but the molecule on the whole is non-polar because we have no north, we have no south, there's not one pocket that's negative and one pocket that's positive. We kind of have this even distribution due to the linearity of the molecule where our polarity cancels out. All right, so these are the three examples then of how we can get polar and non-polar examples, or cases in our molecules. So anytime that we need to figure out the polarity of a molecule, first job is to draw it out. Once you have it drawn, we must establish what the geometry of the molecule is. Since we can see clearly here, the geometry of the molecule is what gives us the difference between a polar and a non-polar molecule between water and carbon dioxide, respectively. So we need to know the shape. Once we know the molecule's geometry, and we observe the electronegativity table, we can figure out whether or not the bonds are going to be evenly or unevenly spread out across the molecule. We can figure out if we're working with something polar or something non-polar as a result. All right, so one really awesome phenomenon or set of characteristics that arises from the polarity of a molecule is how it interacts with a different molecule. Right, if we have two tiny magnets sitting next to each other with north ends and south ends, they are going to arrange themselves in a way that the north and south can attract together. The same thing happens with molecules. The more similar their means of attraction, the easier it is for the two to interact together. So this is sort of like our bridge between molecules and chemical reactions. Before we form a chemical reaction, we need to know what physical interactions are possible between molecules. All right, so to set these intermolecular forces that we are about to discuss apart from what we have discussed already, it's going to be important to define what an intramolecular force is. An intramolecular force is an interaction that occurs within a molecule. Right, so we can think of an intramolecular force as being something that is like introspective. Right, we have to look within ourselves. The molecule has to look within itself to figure out what's holding it together. The different types of intramolecular forces that we've talked about so far are ionic bonds. Right, these occur between two different ions or a metal and a non-metal as they come together. We have discussed polar covalent and polar non-covalent bonds, which arise from the interactions of non-metals with non-metals in both cases. And last but not least, we have somewhat in lab kind of addressed what metallic bonds are, which a metallic bond is a combination of a metal and a metal coming together. Now, the strongest emphasis for sure that we have had so far in general chemistry is that with the ionic and the covalent bonds. And these are all types of, again, intramolecular forces. They occur within the molecule and hold the molecule together. These are the introspective forces that keep matter whole. these are distinctly different than the intermolecular forces. Right, so the only difference in this word is the ER versus previously it was an RA. Right, so intramolecular forces are like the introspective forces. Intermolecular forces are like the interstellar. They go out from one thing. They are looking at the interactions between separate molecules. Things that hold molecules together to form macroscopic pieces of matter. We can think of, as an example, these Legos as being a representation of molecules. So let's say we have one water molecule, we have another water molecule, we have a third water molecule, and the interactions as these like Legos snap together are what define the intermolecular forces. So intramolecular forces are like the covalent bonds holding the one Lego together as a unit, and as one unit interacts with another unit, this is the intermolecular force. There we go, intermolecular force. We also call these forces IMFs. The different types of intermolecular forces that we are going to be defining in this lecture are known as ion dipole forces, dipole-dipole forces, induction forces, and dispersion. There are so many more intermolecular forces than this. The more advanced, though, intermolecular forces we are going to be saving for higher divisional chemistry courses. So again, this is kind of where we're drawing the line between general knowledge, general chemistry, and more advanced knowledge. So these are going to be the four that we're going to introduce in the lecture here today. And again, these are all of the intermolecular forces that exist between two separate molecules. Just as though we, move out from the planet into interstellar space, these molecules are going to be looking outside of themselves to find something else to interact with. All right, the ion-dipole interaction is going to be the first that we talk about. By definition, this is an electrostatic interaction between an ion and a polar molecule. Hence why we call this an ion-dipole moment, or an ion-dipole interaction, is because it's an interaction that forms between an ion and a polar molecule, which has a dipole moment. Right, so the name is pretty descriptive. It tells us what two different forms of matter are coming together to interact. Ions, we know, have charges, right? We can take an ionic substance like sodium chloride and break it down into sodium plus and chloride minus. Polar molecules also have positive and negative charges, right? Hence where the dipole definition comes from that we just discussed. So what we have illustrated here is a water molecule, H2O, inside of what is known as an electrostatic potential map. So what this map tells us is the distribution of positive and negative charges in the molecule. Red corresponds to a partially negative charge. So we can see that this oxygen really has this partially negative charge kind of encompassing the entire, again, kind of top half of the molecule, which is what we expected. And the hydrogens down below are kind of coated in this greenish bluish hue. Greenish bluish is a representation of partially positive charge. So again, our dipole moment cuts this molecule from top down since we have the north end here and the south end here. Negative up on top, positive down below. The distribution of the partially negative and partially positive, though, is what allows water to interact with either sodium or chloride, which also have positive and negative charges. This is what it means to form an electrostatic interaction. Electrostatic interactions are those caused by charges. So positive will attract negative, and negative will attract positive. This is actually what allows salt to dissolve in water in the first place. If we take sodium chloride, right as a crystal, as just a substance, like you're in your kitchen, you dump it into some water, it will dissolve because the sodium plus ends up being surrounded by all of the little partially negative oxygens, of which there is an abundance of that inside of water, right? Especially if you're just adding like a teaspoon of salt to a big pot of water. There's so much water to go around. All of these partially negative oxygens are going to stabilize the sodium. And our chloride is going to be surrounded by the partially positive hydrogens, which again are going to be readily abundant, assuming that we've added the correct ratio of like, this way, oxygen, of salt into our water. Just get rid of this one little thing. Don't want to be confusing. All right, so the intermolecular force itself, where is it? The intermolecular force, which I'm going to draw in red, are the interactions that are caused, right? The attraction that is caused by the partially negative with the positive, or the partially positive with the negative. Each of these little red dotted lines represents the intermolecular forces that arise, the attraction that arises between our water and our salt ions. Similarly, we can bring together two different polar molecules, and in much the same way, we will see the negative and the positive attract. We call these dipole-dipole interactions, since we have one polar molecule with a dipole moment interacting with another molecule that also has a dipole moment. These molecules may be the same, like it might be two different waters coming together, or they might be different. It might be something like water and dichloromethane coming together. What's important is that the two molecules both have polar moments, which will give them dipole moments. Now, what I have written here, that these interactions are not necessarily dipole-dipole, is more of like a physics disclaimer. I sometimes have students in my class who are like intended physics majors, and this is more of like a disclaimer for them. So if you're also more of like a physics student, or you have more experience with physics from high school, let's say AP Physics, this description is going to mean a lot more for you. If you are going to be taking physics soon, this is still going to be an important disclaimer. What I mean by not necessarily dipole-dipole is in physics, it is stated that the most stable interaction between two different dipoles is a perfect alignment of the dipoles. If this were true, we would expect to see the north end of a water molecule perfectly align with the south end of a water molecule, and we would see all of them aligning with their electric fields like so. However, as is illustrated on the right, and as I will also kind of recreate here, the molecules don't actually align perfectly based off of their dipole moments. Instead, what we end up seeing is an alignment based off of where the partially negative and partially positive are. So a partially negative oxygen will align with a partially positive hydrogen, and a partially positive hydrogen will then suck in another partially negative oxygen. So we don't actually get this nice alignment along with the electric fields. We end up with this more like zigzaggy kind of pattern, as positives and negatives in the molecule will explicitly attract one another. This is also what we can see in the diagram here on the right, where the oxygens and hydrogens are a little bit more proportional to like actual size. Oxygen is a larger atom than hydrogen is, just due to the nature of it having a larger atomic shell, right? N equal to 2 as opposed to hydrogen's N equal to 1. The arrangement of the water molecules we can see here is exactly what I just described. We have the hydrogens attracting the negative oxygen, hydrogen here attracting a distant negative oxygen. We can always see that the lines are kind of connected between oxygen and hydrogen. And again, each of these dotted lines is what represents the intermolecular force of a dipole-dipole interaction. So we have the intramolecular forces holding the hydrogens and the oxygens together, and then we have the intermolecular force holding two separate water molecules together. There is a special case within the intermolecular force known as the dipole-dipole interaction. This is known as a hydrogen bond. These are very, very special bonds. These bonds are incredibly strong, very strong dipole-dipole interactions, like surprisingly strong, stronger than what one would expect based off of the types of atoms going into the interaction. Hydrogen bonds are what are responsible for a great number of like incredibly important interactions, at least as we would consider for life. So the interactions between water molecules, allowing them to behave the way that they do en masse, the types of interactions that occur that build our proteins and DNA, these are hydrogen bonding interactions. And their surprising strength is what gives an incredible amount of stability to the molecules like proteins and DNA as they form. A hydrogen bond, by definition, is another type of electrostatic interaction, so we have positives and negatives attracting one another. These positives and negatives, though, are very special because they arise from two very polar molecules that are each going to contain some kind of nitrogen to hydrogen, oxygen to hydrogen, or fluorine to hydrogen bond. So in molecules like NH3, H2O, and HF, we can see that there is an incredible distribution and a very distinct distribution between the partially negative up on top, which we can see gets stronger as we go all the way from left to right with HF, and the partially positive down below is also very distinct and very sharply separate from this partially negative up on top. And again, that sharpness increases as we go from NH3 to HF. So because of the incredible separation in charge, because of this very distinct partially negative and partially positive, what we end up with is a phenomenon where, let's say, we have two different water molecules coming together, which is the exact same example as what we just used, but because we have an OH bond here and an OH bond here, the interaction between the OH and the OH, due to the extreme polarity of this bond, is going to give us a really, really strong dipole-dipole force. Right, so hydrogen bonds are a form of dipole-dipole interactions. Not all dipole-dipole interactions, though, will be hydrogen bonds. Again, squares can be rectangles, not all rectangles are squares. So if you observe a dipole-dipole interaction where both of the bonds involved are either an NH and or OH and or FH, we are going to end up with a very, very strong dipole-dipole force, which we could call a dipole-dipole intermolecular force, or we could refer to it as a hydrogen bond. Shorthand for hydrogen bond is H bond. All right, so the interactions between two different water molecules can contain, or rather can be labeled as, two different things, and that's totally fine. It's going to be important in the hydrogen bonding cases to acknowledge when this very special type of dipole-dipole interaction is possible. So this is why we introduce it. All right, so let's look at an example. Intermolecular forces are important because they give matter certain characteristics that allow them to either physically interact with each other or not. For example, vinegar is very easily mixable with water. The two are going to mix together and create, as we would observe, going back to a definition from chapter 1, a homogeneous mixture. Right, this may be vinegar mixed with water, but it all just looks clear and colorless. It all just looks the same. It all looks evenly mixed. There's no layering that's occurring. And we would assume or conclude that this is occurring because at the molecular level, vinegar and water can interact with each other in a very strong and attractive way. What we are going to do is illustrate the molecules and figure out what electrostatic intermolecular forces are possible. There may be more than one listed. In fact, there's going to be more than one listed. So I'm going to encourage you to draw out the structure for vinegar. If you're not exactly sure what this looks like, you can always look it up online and partner that with water and see in what ways you can configure these two molecules together and what kinds of intermolecular forces can you get as a result. All right, welcome back. Let's come together. We'll start by drawing vinegar. Again, if you're not sure what this looks like, you are totally free to look this up online. I am just going to illustrate my little vinegar down below. So we have a CH3, meaning that there's a carbon with 3 hydrogens coming off of it. COOH, is going to be off of this first carbon, a little carbon right here, double bond to one of our oxygens, and then an OH, single bond to another, single bond to the oxygen after that. Now, this structure is definitely more complicated. As a disclaimer, like particularly if you're in my class and you're like, oh my gosh, we never talked about large structures like this, totally fine. They're going to be a little bit more apparent as we kind of get like general practice with them as we go. So if you had to look this up, no shame. I would never shame anyone for needing a little bit of extra information. All right, the vinegar molecule, our acetic acid, as it is drawn below though, we can kind of start picking out where there's going to be polar moments, non-polar moments, and that's going to tell us how this molecule will potentially interact with water. All right, so I'm going to switch colors for contrast. Contrast is becoming even more useful. So carbon to carbon is going to form a non-polar bond. Similarly, carbon to oxygen forms a non-polar bond. So we have an entire kind of non-polar half to this molecule, which is going to have some really important implications that we'll talk about in a little bit. Carbon to oxygen, as we discussed earlier with the case of carbon dioxide, does form a polar bond. So we're going to get a polar bond in this direction, a polar bond that does not perfectly cancel out in this direction, and similarly, oxygen to hydrogen is another very polar bond, so we have a polar moment in this direction. So we're going to end up with kind of two areas of partially negative charge here, a slight partially positive charge here, and definitely a partially positive on top of this carbon here. Now again, because nothing is like linearly distributed, in 3D space, we are not actually going to end up with any canceling of these negatives and positives. We're not going to have a case like carbon dioxide. Let's observe where the positives and negatives are. And we're going to start adding some water molecules around these locations. So the first kind of positive-negative dipole moment we can see here, there's going to be positivity left on the carbon, but it's kind of crowded in there. So let's add a hydrogen, oxygen-hydrogen combination right here. Right, so partially negative oxygen is going to attract a partially positive hydrogen. The next thing that we have to assess, since we do have a dipole-dipole moment, a dipole-dipole bond, dipole-dipole intermolecular force, which is what is right here with this dotted line, we have to ask ourselves, is this a hydrogen bond? Right, so we have one dipole-dipole interaction, but is this also a very special dipole-dipole? The way that we answer that question is by observing both of the bonds that are coming together that caused this dipole moment. The first is an OH, which is one of the requirements to form a hydrogen bond, right? We have great polarity here, a great charge distribution, great charge separation. Carbon-oxygen, though, does not qualify. The electronegativity difference between carbon and oxygen is not so great that we would expect to see a very, very strong dipole-dipole interaction. So for that reason, this intermolecular force with the water coming off of this double bonded oxygen is just going to be labeled as a dipole-dipole interaction. All right, the other polar moment that is down here, down below with our partially negative oxygen, the partially positive hydrogen, we can interact with another water molecule with a hydrogen coming in close contact with our partially negative oxygen, oxygen here, hydrogen, partial negatives. So we can start to get some really nice stacked interactions where a hydrogen's going to attract an oxygen, oxygen's going to attract a hydrogen. We're going to end up with two dipole-dipole bonds here if the molecules arrange themselves in the perfect way. Is this going to happen guaranteed? Maybe, maybe not, right? This is in a liquid state. So these molecules will be constantly moving past one another, right? That's what it means to be a liquid, is that these things are going to be slipping by one another. But the intermolecular forces as they form are going to be strong enough to keep this in a liquid state and prevent it from moving into a gaseous state, or prevent it from layering even. All right, so the interactions that form between this oxygen and hydrogen and this oxygen and hydrogen are going to be classified as a dipole bond, dipole-dipole intermolecular force. And now we can also ask ourselves that special question, does this count as the hydrogen bonding case? Well, we do have an oxygen and a hydrogen interacting with an oxygen and a hydrogen. I don't know why I said that's so weird, hydrogen. Since we do have OH bond interacting with OH bond at long distance along these dotted lines, we are also going to have a hydrogen bond. This dipole-dipole interaction is the special case where we are specifically working with a hydrogen bonding intermolecular force. Now, hydrogen bonds are, again, really strong dipole-dipole interactions. They're very, very stable. We can explain the homogeneous mixture forming between vinegar and water because of the strength of the individual intermolecular forces that are forming here, here, and here. And as the molecules slip past one another, we also have the chance to form another dipole-dipole interaction kind of here. This water can move around and still interact with this oxygen here, right? There are plenty of locations as the molecules slip by one another where we are going to form stable interactions. All right, so this brings us to where I have very strong feelings about intermolecular forces, particularly where I disagree with general chemistry textbooks. And this is my class, and I choose to teach it the right way. Most notably because I am a theoretical inorganic chemist. This is what I got my PhD in, and I don't think it's difficult to teach the more correct definition of what a dispersion interaction is to students. So here's my disclaimer. According to the textbook, and this is going to be true, like 99% guaranteed for whatever Gen Chem textbook you look at, dispersion is described as a temporary electrostatic interaction between two nonpolar molecules. This is not true. The reason why we can even just, as a brief kind of example, demonstrate how it's not true is if one nonpolar atom were to come into contact with another nonpolar atom, the way that, again, the textbook describes this potential intermolecular force that would hold these two things together is by saying that one of these nonpolar atoms will spontaneously gain a partially positive end and a partially negative end. This will cause another nearby nonpolar atom to respond, and its electrons will move accordingly, so we have negatives and positives coming together, and this is what they describe as a London dispersion force. The reason why this is nonsense, to me, statistically speaking, is if these are temporary dipoles, they are going to be so fleeting and so statistically unlikely to form, there is no way that we would end up with strong dispersive interactions that we see experimentally. This description is good enough in high school, but as you continue at the college level, you are going to come into contact with cases where this description of dispersion is just obviously not true. And there are plenty of foundations we build in general chemistry that are mostly true, but not quite true, just to get us most of the way there so you can continue and it's fine. But no, dispersion is something that I am going to teach correctly. If this is not what dispersion is, what is it? Well, in order to answer that question, we must first address how is it that nonpolar and polar molecules interact with each other. Only after that can we really get into the true meaning of dispersion and describe how two nonpolar molecules interact with each other. An induced dipole interaction is an intermolecular force that occurs between something that is ionic/polar and another molecule that is nonpolar. So nonpolar species can and do attract with things that are polar. We're just going to have to force this nonpolar thing to have a dipole moment. Now, what sets this example apart from the previous case that I disclaimed as nonsense is that in order for something that is nonpolar to gain a polar moment in a real meaningful way, we need to have something else that has a dipole moment nearby. Something that will always have a partially negative and partially positive charge on it, stabilized, always there. This will allow for the electrons in one of these molecules, this polar case, to influence the electron density on the nonpolar case, again in a long-lasting and meaningful way. The impact that a polar molecule has on a nonpolar molecule is proportional to the polarizability of the nonpolar molecule. Polarizability, by definition, is the tendency of the electron density to be distorted. And this is found to be proportional with atomic size. The bigger the atom, the less of a hold it has on all of its electrons, and the easier we can just push them around, right? Electrons are dynamically moving. So if the electrons in the bond between two oxygens are moving like so, if we suddenly brought in a negative charge here, well, the electrons, which are also negatively charged, are going to start hanging out over here more. This is going to allow a partially negative charge to build up on one side, and as the electrons leave that first oxygen, a partially positive charge will build up on the other. This is what leads to a dipole-induced dipole interaction illustrated down below, where the really strong and distinct partially negative charge on the oxygen in water is going to force or induce a partially positive charge on the nearby oxygen and a partially negative charge on the faraway oxygen. And again, the reason why we need a polar and nonpolar combination is we need something with a definite negative charge to really allow and force this induction to happen. One analogy that I use to try and describe again, or just reiterate, how dynamic these electrons are involves sheep and wolves. So let's say we have a really nice big field. And inside of this field, which is going to represent our nonpolar molecule, we have this nice little even distribution of sheep. These sheep are going to wander around, kind of aimlessly, evenly distributed, right? There's nothing kind of like coaxing them to one side of the molecule or the other. Here we have a really nice nonpolar distribution. Each of these sheep represents electrons inside of the nonpolar molecule. So as they meander around in kind of this even distribution, we're not going to have any one side of the field or molecule that's positive or negative. Well, in order for these sheep to really move from one side of the molecule to the other, we're going to have something that's going to force them to move, right? Another field of nonpolar sheep nearby is not going to cause any of these sheep electrons to really move from one side to the other. We need something that's really going to scare them into moving. This is where the wolf comes in. Here's my little wolf. He's got his big ferocious teeth. He is hungry. He is a mean wolf. He is looking for something to eat. Here are its little feeties. Here's his big old tail. This wolf represents our water. This is a molecule that has a definite, distinct dipole moment, and its teeth represent that partially negative charge that is present inside of the water. As the wolf approaches the fenced-in area where the sheep are going to become alerted to this wolf, and they're going to instinctually try to get away. As the sheep flee from the left-hand side to the right-hand side of the field, again, where these sheep represent all of our electrons, we're going to end up with a partially negative buildup on the right-hand side of our fenced-in area, again, representing our nonpolar molecule. And what will remain is kind of this empty space where there is a little positive nucleus here. That positivity is going to be a little bit more exposed as the sheep flee to the right-hand side. Right, two fields of sheep right next to each other are not going to cause any type of meaningful, long-lasting enough electrostatic interaction. Even if it might occur, it doesn't really have any physical meaning, statistically speaking. We need something with a definite positive and negative charge to really exacerbate these electrons and push them distinctly from one side of the nonpolar molecule to the other. We need a wolf to scare the sheep. Once the wolf has thoroughly scared the sheep, the positive and the negative that remain, so the negative on the wolf, the positive that is left behind from the sheep fleeing, is going to cause an electrostatic attraction, right? Negatives and positives attract. This attraction, coming back to our illustration on the right, is the dipole-induced dipole interaction. Something with a dipole has induced a dipole on another molecule that normally doesn't have one, and now the positives and the negatives are going to attract. This type of interaction is labeled as temporary because once this water molecule leaves, right, like once the wolf gets bored and decides to go away, the sheep will redistribute back across the field. The thing that is normally nonpolar will return to being nonpolar. All right, so this is our description for the induced dipole intermolecular force, which by definition is also electrostatic in nature. So the electrostatic, positive and negative attracting kind of intermolecular forces that we have discussed so far are ion dipole, dipole-dipole, hydrogen bond, and now the induced dipole interaction. Each of these things is electrostatic in nature. Dispersion is the one intermolecular force that we are going to introduce that does not function based off of electrostatics. It is not an attraction based off of positives and negatives coming together. Dispersion is what we call an exchange interaction. An exchange interaction, by definition, relies on the existence of electrons inside of your molecules. And an exchange interaction is an attraction, or admittedly, sometimes a repulsion, but we're going to be focusing on the attractive component. It is an attraction that is caused by the exchange of electrons. Now, at the general chemistry level, we tend to think of or describe dispersion as being existent between only two nonpolar molecules. So if you have one nonpolar molecule and another nonpolar molecule coming together and interacting with each other, this interaction in between is what we commonly call dispersion. And again, the textbook's description is a little bit nonsensical. So how can we actually describe what dispersion is using the more accurate definition of an exchange interaction? Well, dispersion is, or functions, more like a weak covalent bond than anything else. And again, for anyone who happens to be watching this that is a little bit more advanced in chemistry, bear with the generalizations. But again, I'm trying to describe dispersion in a more accurate way than what the general chemistry textbook does. All right, so let's use these two bromines coming together as an example for what dispersion is going to look like, how we can think about it. Now, bromine, a pure sample of it, we can gather in a test tube, and it is actually in liquid form. So what this tells us is that the molecules that are coming together in this collection are actually attracting one another. They are going to be additive, coming together and stabilizing each other and condensing into this liquid state. However, each bromine, which is formed by the covalent bond that is existing between two different bromine atoms, each of these with their own sets of lone pairs around them, this is a nonpolar molecule. Nonpolar, right? We have no partial charge on one side of the atom or molecule, no partial charge on the other. It's the electron pair, this bond, this covalent bond between the bromines is being evenly shared as it oscillates back and forth. Now, as another bromine approaches in close distance, each of these bromine atoms inside the molecule also with their own lone pairs and the bonding pair evenly fluctuating back and forth. As these two things come together, we have to consider the dynamic behavior of the electrons. See, a covalent bond is the sharing of electrons between two different atoms inside of one single molecule. What dispersion is the sharing of electrons, which are dynamic, between two separate molecules. Because from the perspective of one single electron, it's not like this electron thinks of itself as belonging to bromine. There's nothing special about bromine. Each of these electrons inside of these molecules is literally the exact same. And all they are looking for is a positive nucleus. Well, if these two bromine molecules are separate, this one electron is going to continue hovering back and forth between these two nuclei inside of these two bromines. As soon as another bromine atom shows up nearby, though, this electron is going to see it at a relatively short distance and is also likely to flip over to the other bromine instead. Well, if the first electron's gonna do that, this second electron is going to start acting as though it's also in an electron pair with the bromine on the left, and also flip back and forth. So we end up with something that looks like a covalent bond description. The big difference, though, why this interaction, why this intermolecular force is so weak, is because the distance between the two molecules, distance between these two molecules is longer than within. In other words, and I'm just gonna change color for the sake of a really good contrast for this last point. Let's get this blue up. This bonding distance right here is longer than this bonding distance right here. And the electron that is present on this bromine is going to be stabilized by whatever nuclei are the closest. And so this electron is going to hover back and forth between the two bromines inside of the molecule way more frequently than it would leave. However, this distance, although it's longer than the covalent bond, is still short enough that the electron can see the bromine on the right-hand side and on occasion just flip sides, change teams, if you will, and in the process is actually going to stabilize the interaction between these two different bromine molecules. So as electrons flip back and forth, as they get juggled between these two different molecules, we can think of the interaction that exists as being similar to that between two actual jugglers in some type of performance. As these two people are throwing, I don't know, in this case I'm just illustrating some balls, but you know, it could be chainsaws or fruit or bowling pins or whatever they're juggling back and forth. These two people and their positions, their placements, are going to be held in place by this routine, by them juggling these items back and forth. If either one of these people would leave, suddenly all of these things that they're juggling would just crash to the ground. So the existence of the interaction of this juggling act necessitates that there be two jugglers nearby. The most stable form of this type of interaction occurs within a molecule, but it can also happen between two different molecules at a longer distance. All right, so this is one way that we can describe dispersion that's a little bit more accurate, that's a little bit truer to form. It requires our acknowledgement that electrons are dynamic, but at the same time, this dynamic nature of the electrons is what allows them to move around. This kinetic motion is what stabilizes the atoms at longer and shorter distances. Now, something else that's really cool about dispersion is that it doesn't only exist between two nonpolar molecules. Technically, if your molecules have electrons, dispersion is present. Dispersion can be there. So as, let's say, for example, we bring two water molecules together at shorter distance, we've already talked about how this interaction forms a dipole intermolecular force due to the polarity of the two molecules. And more specifically, we can form a hydrogen bond because the polar difference between O and H is so strong. The dipole-dipole IMF between these two water molecules is going to be incredibly strong. However, because both of these water molecules also have electrons, we can also add dispersion into the mix. So molecules, as they come together, in conclusion, can form just one intermolecular force. They could have two intermolecular forces stabilizing them and bringing them together, or they could have three. They could have as many as what the construction of the molecule allows. And so long as your molecules have electrons and those electrons are moving, you have the chance for these electrons to flip-flop between the two different molecules, and dispersion can technically exist here as well. Now, is the interaction of dispersion as strong as the dipole-dipole force, or is it as strong as the hydrogen bonding force? We'll talk about that in a little bit. But first, let's compare and contrast our previous vinegar and water example with something else that really allows for a dissection of dispersion, in contrast to these other forces. Dispersive intermolecular forces can at times be competitive with electrostatic intermolecular forces, things like dipole-dipole or hydrogen bonding interactions. So for example, if I ask you what intermolecular forces are occurring between oil, and here we can see the chemical formula, I believe this is for canola oil, and water. If we put these two things together, observationally, we would see a heterogeneous mixture occur because the oil is going to float on top of the water. My question to you is, what intermolecular forces occur between oil molecules and water molecules that lead to this heterogeneous mixture? All right, welcome back. Hopefully you took the time to kind of observe these molecules and pick out what intermolecular forces stabilize these molecules. Now let's start with an observation of this very long oil molecule, where at the vertex of each of these like little triangular points is a carbon. And each of these carbons is also going to be surrounded by the necessary number of hydrogens to complete their octets. So each of these central carbons is also going to be surrounded by a certain number of hydrogens. I'm not going to spend the time to illustrate each and every one, but you get the picture. Each one of them is going to have a complete octet. Now, carbon to hydrogen, as we have already talked about, is a non-polar bond. So within this oil molecule, we have a polar section where this one carbon bonded to oxygen, or this carbon bonded to oxygen, is going to result in a polar section. However, the further and further we get away from that polar section, the more and more non-polar our molecule begins to appear. So we would say that we have a polar section on the left, this little section, and the rest of this molecule is going to be predominantly non-polar. So we actually have two natures existing within this one single molecule. It's like the dichotomy of man, only it's the dichotomy of molecules instead. Well, if we allow for two options, let's say either another water molecule or another oil molecule is going to approach this oil molecule, or a water molecule will approach this oil molecule, which is going to be more stable in interacting with the oil? Well, if we illustrate like a water molecule approaching, water we know, again, is a very polar molecule, and it's capable of forming a great number of electrostatic intermolecular forces. Things, again, like those dipole-dipole forces, etc. And so the polar nature of this water molecule means it's going to be stabilized predominantly by forming the electrostatic category of intermolecular forces. And so water would be able to interact with the oil, but only in this one little section. A water molecule would only really be able to stably interact with this section here on the left. This water is going to form probably a dipole-dipole force, hydrogen bonding if it's with this little OH specifically, but really we'd only be able to form like one or maybe two stable intermolecular forces between water and this oil molecule. And technically, yes, we could form probably an induced intermolecular force, an induced dipole force over here on the right-hand side, or maybe even some type of weak dispersive interaction here on the right-hand side. However, if we contrast that option with the addition of another oil molecule, OH to carbon, double bond to oxygen, and I'm just gonna draw a big old ziggy-zaggy, because who got the time? The oil molecule here is going to have the exact same construction with a little polar section here and a huge non-polar section here. Non-polar bonds are predominantly stabilized by dispersion. The electrons are not being pushed in one direction or another due to the polarity of the bonds. The electrons are allowed to more freely fluctuate. And because the electrons are able to more freely fluctuate at close distances, what we're going to end up with is a area where dispersion is going to be more likely, right? We're not going to have electrons being pulled into the center of the carbon or held too tightly to the hydrogen, which is going to allow for an easier means of dispersion. But we're not just going to get dispersion between these two single hydrogens. No, no, no. Anywhere where the hydrogens are going to be coming in closer contact with each other, hydrogen here, there's going to be plenty of locations across this entire non-polar tail of the oil molecule where we can end up with long-distance dispersive interactions illustrated here. So between forming one or two stable electrostatic intermolecular forces with water, or forming a large number of dispersive and stabilizing interactions between these two different nonpolar tails, oil, as it turns out, is way more stable interacting with other oil molecules. This is because the construction of the molecules are much more similar, and again, we're going to be able to form a ton of attractive dispersive interactions. So oil is going to want to stick with oil, hence why we see oil floating on top of the surface of water. Now, oil and water can, again, somewhat interact with each other. It's not to say that the interactions between these little polar sections of the oil molecules and the water are completely non-existent. That's what allows for this stable interaction between oil and water. We do not see a chemical reaction occur between oil and water. The two just kind of hang out one on top of the other. However, this attraction is not so strong so as to lead to a homogeneous mixture. Instead, we end up with a heterogeneous mixture. Oil sticking with oil through the formation of dispersive interactions, and water sticking with water because we can increase the number of really stable electrostatic intermolecular forces. The intermolecular forces that we have introduced today, ion dipole, the hydrogen bond, which is a special subset of the dipole-dipole, induced dipole, and dispersion, do not all have the same strength. They all have varying strengths. And in general, if we were to compare one ion-dipole interaction, let's say, in contrast to one dispersion interaction, we would find that the stability between an ion and a molecule that is polar with a dipole moment is going to be much stronger than dispersion. And so here's the relative ranking. Ion dipole's the strongest. Hydrogen bonding is a stronger subset of the dipole-dipole case, so that's why it's listed above. Induced dipole comes after that, and dispersion is underneath. Ion dipoles can only form between an ion and a polar molecule. Hydrogen bonding and dipole-dipole interactions form between polar and polar molecules. Induced dipole is between polar and nonpolar. And last but not least, we have the bare minimum interaction, which can technically occur between everything, but it was first discovered when trying to observe and figure out how nonpolar and nonpolar things interacted with each other. And there we go. I just quickly filled in the rest of the polar, nonpolar, polar, polar, ion polar in reverse respect. All right, so again, the relative strengths of the single intermolecular forces are just that. If we are observing one dotted line connecting two different molecules, one where it happens to be ion dipole, the other that happens to be dispersion. However, as I've also been discussing thus far, our intermolecular forces can kind of stack on top of one another. We rarely ever only have just one intermolecular force, unless we are looking at nonpolar and nonpolar molecules coming together, because the only type of IMF they can really form with each other is dispersion. This would mean if dispersion was truly the weakest as two nonpolar things came together, if we were just looking at single IMFs, like if the intermolecular forces didn't stack, is what I'm saying, all nonpolar species, all nonpolar collections of molecules should have the exact same stability, they would all have the exact same volatility, the exact same boiling point as they were forced to change phases, but what we see is that's not actually the case. For example, if we compare two pentane molecules, each of these has the chemical formula of C5H12, it's just that the arrangement of the atoms in the molecules are different. What we find experimentally is that the boiling point of the first molecule, the first arrangement, is actually higher than the boiling point of the second molecule. All right, so this boiling point phenomenon is dependent on the strength of our intermolecular forces for the following reason. Materials as they exist in a liquid state, right, are attracted to each other by these intermolecular forces that we've been talking about. Now, the molecules might be sliding past one another, but they're still going to be in close contact with other molecules, hence having some degree of intermolecular force stability, which is keeping it in a liquid state in the first place. In order for something to boil, what this truly means is that we are taking one molecule and separating it from everything else. In order to take a molecule and separate it from the bunch, we're going to have to cut ties, cut all of these intermolecular forces around it. So the stronger the intermolecular forces, the more energy we have to put in to separate this one molecule. The more energy we have to put in corresponds to needing a higher temperature to boil. So if we observe a substance that has a high boiling point, what this means is that there are stronger intermolecular forces between the molecules holding things together. In the cases where we have lower boiling points, we're actually observing the case where we have weaker intermolecular forces holding the molecules together. And in this pentane example, where the only difference is the arrangement of the atoms in the molecules, we can get a really good explanation for how the number of intermolecular forces also plays a role, like how the IMFs stack on top of each other. The additive power of intermolecular forces, if you will. So in the pentane example on the left, we have this like kind of linear arrangement, right? The carbon, 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 carbon are all kind of spread out, and they're all surrounded by these hydrogens, all of the octets are satisfied, etc. How this looks in 3D, we can kind of see up above. It looks like a weird kind of caterpillar creature, but it's more of an oblong shape, right? So we have ovals present in both cases. What this does is increase the surface area of the molecule, meaning that if these two things were to come into contact with each other, as they would in a liquid state, there are more points of contact between the hydrogens, which gives us a greater degree, more dispersion, a greater degree of dispersion. Since we have more dispersion, we have a stronger resulting intermolecular force and a higher boiling point as a result. If this were a nonpolar and a polar molecule coming together, we'd also have the chance to form induced dipole interactions, or polar and polar molecules like water coming together, also being able to stack up on top of this dispersion and even increasing our boiling point more. In contrast, if we observe the arrangement of pentane on the right, where we have more of like a spherical structure, what we have done is created a molecule where we have a decrease in the surface area. And this decrease in the surface area, since spheres are technically the geometry that has literally the lowest surface area we can get in three-dimensional space, we have decreased the points of contact that are possible between these two molecules. There is less dispersion as a result, right? There are fewer points in contact where the electrons can just kind of swap places like this. With fewer points of contact, we have less dispersion. With less dispersion, we have a weaker combination of intermolecular forces, which gives us a lower boiling point. It takes less energy for us to cut these ties and separate these two molecules from each other and introduce them into a gaseous state. So the relative strengths of just comparing single intermolecular forces we can see here on the left, but as we move forward, it's also going to be important to recognize that the additive power of intermolecular forces is also going to give rise to very special physical properties such as boiling point, melting point, etc. Whew, that was a longer lecture with plenty of at least initially disparate topics that all came together. So we have bond polarity that comes into play in this conversation. We have molecular polarity. We have geometry. And then, as we moved through the lecture, we began to really digest and dissect what are the results of having these polar versus nonpolar molecules and all of the different intermolecular forces that can arise between molecules due to the differences in polarity, electrostatics, and the nature of the electron itself. So with so much information that I have given your way, please take the time to digest everything that we have talked about, most notably the discussion of dispersion. At the end of the day, if you can understand and remember that the interactions that occur between molecules as electrons swap places, that is what we call dispersion. That is going to be what you need to remember, and at the very bare minimum, nonpolar molecules will interact with other nonpolar molecules via dispersion only. But with that, no more tangents, no more descriptions, just take the time to digest. Please work through these example problems if you feel the need. If you have any homework, please double check and do your homework, and until next time, class is dismissed.